Hello, good to Budiya. So today we are going to study class 10's magnetic effect of current. If this topic hasn't been understood by you yet, तो इसका एक ही कारण हो सकता है that maybe you have only watched it's only one short video till now. Today is coming masters gunshot video. The meaning of gunshot video is every single topic मैं हलवे की तरह बना के तो मैं प्यार से मैं खिलाऊंगा. Everything will be understood. 100% NCERT will be covered inside this lecture. I will make you practice many boards previous year questions, repeated questions exactly as they are inside the lecture. I will settle every single topic in your mind. And after watching this lecture, whether it is your pre-board or school exam or board exam, you will not find a single question outside of this lecture. तैयार हैं आप? Let's start this chapter. We will study with fun, enjoy and understand everything. An important thing that at this timestamp the question will appear whose answer you have to tell in the comment. जो लोग सही आंसर बताएंगे 10-15 गुड्डू कुड़िया from those who give the correct answer at the end of next lecture. I have taken the name of the winners of the previous lecture. शुरू करें lecture. Are you ready? At this timestamp is the question whose answer is to be written in the comment. Okay, let's start. Come, let's study some basic things. हो सकता है आपको पहले से पता हो, but it has to be used in later in this chapter. First thing, भैया, what is magnet? Everyone knows, master. What is magnet? It is a small piece, that attracts a bunch of keys toward itself. It pulls iron object toward itself. It goes and sticks to the bridge. It sticks to the iron door. एकदम सही है. An object which attracts pieces of iron, nickel and cobalt. Nickel, cobalt has also magnetic properties. So the magnet also pulls it. One topic will come again and again, bar magnet. What is a bar magnet? You must have seen this magnet. You have seen it. Bar shape means a rectangular shape. A rectangular shape magnet, it is called a bar magnet. By a magnet has two poles. One is a north pole, one is a south pole. How we will know which is the north of the magnet, which is the south? There is a very basic method. If this is a magnet and its pole are to be determined, then tie it with a thread and hang it. Suspend it freely. The moment you suspend it freely, it will be like this, a little tilted, like this. One end of it will go towards the north of the earth and one end will go towards the south of the earth. The one that go towards the north of the earth will become the north pole. The one that go towards the south of the earth will become the south pole. So a freely suspended magnet rests in north-south direction. Acha, what do like poles do? They repel. If I bring two magnets close, this one north, then what do they do to each other? They repel. If I bring both south, near, it will also repel. But what do unlike poles do? They attract. One magnet's north and the other magnet south. Bring them close, then they stick together. So north and south attracts. North and south repel. Okay. A device comes a magnetic compass. Its use is very frequent in this chapter. What is magnetic compass? It's a round shaped thing. Directions are written on it. Inside it there is a small magnet. What is it? It is a small magnet. This is a magnet. Okay. This magnet's north pole is this and the south pole is this. There is a magnet inside it. And this magnet is the shape of a needle. It is a needle shape. Look, a needle shaped magnet is fitted like this. So that's written. A compass is a small magnet in the shape of a needle. What is it? It is a small magnet in the shape of a needle. What is its function? Suppose you want to find out if there is any magnet around in this room or not. So you take this compass and wander around this room. Where the needle of this compass, it deflects, then there somewhere magnet is there. So it detects the presence of whether there is any magnet nearby or not. How does it deflect? Its needle deflects. It will go this way or will go this way. Okay. The stronger the magnet is, the more this needle will deflect. You are walking with it in the room, walking. You took it under the bed like this and meaning there is a very strong magnet under the bed. The stronger the magnet, the more it will deflect. There are the things written. It detects the presence of a magnet. First thing, or magnetic field. We will study the magnetic field later. Now this is next topic. When a magnet or magnetic field is around, the more will be deflection. Stronger the magnet, more is the deflection. The stronger the magnet, the more the deflection will be. If there is no magnet around it, then tell in which direction will it be? What did it become? A freely suspended magnet. The magnet is inside this. then its north pole will be towards the earth north. The south pole will be approximately towards the earth south. Okay. Now the topic magnetic field has come by. Now what is this? Suppose bhaiya you live in Banaras. If I tell you there is a fight in Delhi, bring the boys. What will you say? No sir, we won't be able to come. Our area is around our house in Banaras. We can fight here. So what is Banaras? It is your field where you can do things nearby. After coming Delhi, your field is finished. The same is the story of the magnet. Suppose this is a magnet. If I put an iron key near it, it will stick. Keep it like that. It will stuck. Keep it like that. It will stuck. Kept it further. Now it is not coming. That means the field of this magnet is getting over. The space around the magnet in which other magnetic material feels a force. By put magnetic material, what will happen? Force will apply on it. Or if another magnet is also kept, what will apply on it to force? So the area around the magnet where there is magnet's dominance, where the magnet can apply force on other things. What do we call that whole area? The whole effect, we call it the magnet's field, we say it. The space surrounding a magnet in which other magnets or magnetic material feels a force, right? The space around the magnet in which any other magnet is kept, it will apply force on it. Or if any iron object is kept, it can apply force on it too. Okay. Now just as force, work, displacement, velocity are quantities, physical quantities. Similarly, magnetic field is a physical quantity. Just like we measure force, we measure mass. Similarly, you are going to study a new quantity in physics from today, magnetic field. Its symbol is capital B. Just like force is represented by F, will also be represented by V. Magnetic field is represented by B. Now pay attention. Magnetic field is beta. It's a vector quantity. Which ones are vector quantities? Which has both magnitude and direction also. So it will have some value and some direction too. First we will study the direction of magnetic field. We have to find the direction of this B. There is a very good way to find its direction. Suppose this is a given magnet. There is a north pole and south pole. Which magnet? Bar magnet. Will there be a magnetic field around it? Yes or no? Absolutely. If it's magnet, there will be a magnetic field around it. Okay. In whichever place I find the magnetic field, in whichever place, magnetic fields, direction I have to find. I'm talking about direction. Direction. By the direction of the magnetic field will be here, 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 here. Where it will be? In whichever place I have to find the direction of the magnetic field. What I'm going to do? I will put a tiny north pole in that place. Imaginary, tiny north pole. Actually, such a tiny north pole is not found. North and south are always found together. Then imaginary, I thought the north pole is kept here. Now I will think, where will this north pole run? Where will it go? Think, will this north repel this north? Absolutely it will. So when this north repel this north, it will throw it this way, meaning this north will run this way. Meaning this become the direction of the magnetic field. What is written? The path along which a free north pole moves. Free north pole is what kind of concept, beta? It is imaginary concept. In reality, there is no such thing as north pole. Absolutely not. The path along which a free north pole moves. It went on this path. Whose direction did it become? B. That is magnetic field. Suppose I need direction of the magnetic field here. What will I put here? I will put a north pole. Now where this north pole run? This is north, this is north. It will repel it. Will it throw it this way? Absolutely. So whose direction did it become? Of the magnetic field. Suppose I need the direction of the magnetic field here. I place the small north pole. This is the south pole. It will attract the north pole. It will run this way. This becomes the direction of the magnetic field. I need the direction here. I place a north pole. It is the south pole. It will attract the north pole toward itself. This becomes the direction of magnetic field. So how do we find the direction of magnetic field? Very important. It has been asked in the board. How do we find it? The path along which a free north pole moves. The path on which a free north pole moves. What is that? Direction of magnetic field. There is one more method. It is simpler. Bring a compass. Bring a magnetic compass in your hand. Now whichever side the north pole of the compass is running, that becomes the direction of the magnetic field. By a compass also a north south both. So bring a compass, whichever direction compass north running, that becomes the direction of the magnetic field. For example, suppose I need the direction of the magnetic field here. So I bought the compass. The compass north ran this way and south this way. So wherever the north ran, that is the direction of magnetic field. Direction in which a north pole of the compass needle moves. Wherever north pole of the compass needle moves. This is the way to find the direction of magnetic field by. Okay. What is the next thing that came? Magnetic field line. Now what is this? It is the same. Which is the direction of the magnetic field? Understand it, the moment similar. Around a magnet, you must have seen lines drawn like this. What are these lines? Actually, you take a magnet in real life in your hand. Do any lines appear around it? No, they don't appear. So this is an imaginary concept. Yes, it is an imaginary concept. What is the concept? It is the same concept as the magnetic field one. It is the same concept. What? Place a free north pole around a magnet and see the very same thing. Place a free north pole and see the direction in which the free north pole ran. That becomes the magnetic field line. Simple. You place the free north pole here. It ran like this. This becomes the magnetic field line. You place the north pole here, where it did run this way, this becomes the magnetic field. So what kind of concept is the magnetic field line? Does it really exist around the magnet? Are there really magnetic field lines next to the magnet? If they don't appear, then they are not. There is a way to see them. I will tell you that later. Okay. So not real, it's imaginary. So what is it? Imaginary lines along which a free north pole or the north pole of compass needle moves. If I place a compass needle here, if I place a compass here, its north was running in this direction. So what did I draw? I draw the magnetic field line. By magnetic field line, just look at the name. Look at the name itself. What would the magnetic field line be telling? It would be telling the direction of the magnetic field. By the magnetic field will be here. Here it will be this way. Here it will be this way. Here it will be this way. So the direction of the magnetic field line is the same as the direction of the magnetic field. By the direction of the magnetic fields was also explained like this. The path along which a free north pole moves. Look here, the magnetic field was like this. Here it was like this. Here it like this. Here like this. Look, it's running here. Look here for a moment. It is same here. Or yes. What are the magnetic field lines? They are imaginary lines along which a free north pole or the north pole of a compass will run. And whose direction is this giving? It is giving the direction of magnetic field. Gives the direction of magnetic field at a point. If I ask what is the direction of the magnetic field at this place, so this is the direction of the magnetic field lines. Is it clear? Now there are some properties we have to study magnetic field. Look carefully at the diagram for a moment. What is this? A bar magnet. The magnetic field line is emerging from north pole. It is emerging from the north pole. And it is entering into the south pole. Does it look like this? It emerges from the north pole, it enters the south pole. So the first point is written here. Emerge from north pole and merge at south pole. They emerge from here and enter here. By think here. Think. Here if I put a free north pole here, this is the south of the magnet. Will it not attract it toward this side? Absolutely it will. So what did it become? Magnetic field line. This become the direction of magnetic field. Say, are you feeling it being understood? Absolutely yes. So where does it emerge from? Where does it go from? It emerges from north pole. It comes and enters the south pole. If we talk outside the magnet, what is the direction of the magnetic field? It emerges from north, emerge, bend into south. It emerged from north, emerge, and bend into south. Let's take a white pen. Everything is made with white, yes. Look, it emerged from north, emerge. Where did it go? To the south. Emerge from north, emerge into south. This one to beta, crossing board from this one, where will it go like this? In the south. This emerge from north, emerge. Where will it go? South. As many lines, carefully. As many lines emerge from the north, the exact same number of lines will enter the south. Count 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Equal. And look here too. 1, 2, 3. 1, 2, 3. Equal. As many lines as you take outside the magnet out from the north, the same number of lines go inside the south. What is the direction of the outside magnetic field line? It is north to south. Outside the magnet, north to south. If I look outside, what is the direction outside? North to south. Now listen carefully. Listen carefully. When it comes to the south, it goes back inside like this. It came like this. It came like this. It came like this, meaning magnetic field lines also exist inside the magnet. Yes, yes, yes. Magnetic field lines exist inside the magnet. It came. Now it completed the whole circle. It emerged from the north. Look, this one. It emerged from the north. It went into the south. Now it came back from south to north. It will go from north to south, back from south to north, from north to south, back from south to north, back from south to north. So what will be their direction inside the magnet? It will be south to north, and outside it will be north to south. That is why it said the magnetic field lines are closed curves. They are not open, they are closed. It emerged from here, emerged from north, merged into south, then back from south to north. So outside north to south, inside south to north. Important concept. Two field lines cannot cross or intersect each other. Two field lines cannot intersect each other. They can't cross each other. Two field lines cannot intercept each other. Say, I'm telling you this, inside south to north, okay. Two field lines cannot cut each other, cannot cross or intersect each other. Now this question is asked a lot in the board's exam. This is important. That by why is it? Why can't two field lines cuts? It is a very simple thing. Suppose two field lines cut each other. Let's assume two field lines crossed each other. I consider this one. One field line went like this. One field line went like this. Here both cut each other. Cut. Now look how big a problem is a cut. If I place a compass at this place where the intersection happened, where the intersection occurred, if I place a compass there, the compass will go mad. This field line will tell the compass to turn its north this way. By what does the compass do? It gives the direction of the magnetic field. Where does the north of the compass run? In the direction of the magnetic field line. So what will these field lines say to the compass? That come this way. It will make its north pole this way. And this one field line is going like this. This will tell the compass to run its north pole this way. Now how can the magnetic compass needle go in two directions? Can it go kachak kuchuk, like this, not like this? It goes only one direction. It cannot go in two directions. By what concept of field line did I tell you? That if you want to draw field line, then what do? Place a compass there. Wherever the north of the compass is running, that is the direction of field line. If I place a compass here, the compass will go mad. It will say this one is saying go this way and I should go this way. And they are saying go this way. So should I go this way? So the compass is here, it went mad. Compass will be confused, it got confusing when a compass is placed there. This field line is saying go this way. So according to this, the north is running this way, isn't it? And according to this, the north is running this way. Arey baap re baap, the compass condition is bad. So this bit is impossible that the compass needle is in two directions. Therefore, two magnetic field lines can never intersect each other. Because if they do, at the point of intersection, north pole of magnetic needle will point toward two direction, which is impossible. Two field lines cannot cross or intersect each other. Why? Because if it happens, because if they do so, at the point of intersection, the north pole of magnetic needle will point towards two direction, which is impossible. Come on, bhai. The story of field lines is clear. It emerges from north pole, it goes to the south. Inside it goes from south to north. And two field lines do not intersect each other. Come on, very good. CBSE 2025, 2022, 2020, 2015. This question was asked repeatedly. Assertion. No two magnetic field lines are found to cross each other. Is this correct? No two magnetic field lines are found to cross each other. True, bhai. This is true. Reason. The compass needle cannot point towards two direction at the point of intersection of two magnetic field line. The compass needle cannot point towards two directions. Correct, by this thing is correct. It cannot point in two direction. Is this a correct explanation? Absolutely, this is explanation. So both A and R are true and R is the correct explanation of A. Okay, this is the explanation of why they cannot cross. Because the north pole of the compass needle cannot have direction toward two sides. The compass needle cannot point towards two directions. Okay, come on. CBSE 2025, 17, 20, what? Which one of the following statements is not true about bar magnet? Come on. It sets itself in the north-south direction when suspended freely. This is true, by. Next, It has attractive power of iron filings. This is also true. Iron filings means iron powder, right? It produces magnetic field line. Yaar, will a magnet create a magnetic field line or not? Absolutely, it will create. It will emerge from north to south. Okay, this is also true. Last, the direction of magnetic field lines inside bar magnet is from north pole to south pole. It become wrong. What is inside? South to north. Outside, north to south. So this is become false. Why? So this become incorrect statement. Come on, bhai, let's move. CBSE 2025, 20, 21, 15, similar question. Assertion. Magnetic field lines around the bar magnet never intersect each other. What is around the bar magnetic field line in this universe? Never intersect each other. Magnetic field line will never intersect. Never. Magnetic field lines around a bar magnet never intersect each other. It's true, bhai. Next. Magnetic field produced by a bar magnet is a quantity that has both magnitude and direction. Correct, bhai. The magnetic field quantity, a bar magnet will definitely produce it. All the magnets produce it. It is such a quantity that has magnitude and direction. This is also true. This is also true. But is this explanation? No. Above it is saying magnetic field lines around a bar magnet never intersect each other. What should have been its reason? Its reason should be because the compass needle cannot point in two directions. But here it's something else. So both are true, but it is not the correct explanation. Both A and R are true, but R is not the correct explanation of A. This is not its correct explanation, but both segments are true. Come on, let's move forward. Now the magnitude of magnetic field has come. The direction is understood. How will we find the direction of the magnetic field? We will put tiny north pole. Whichever side it is running, that will be direction of magnetic field. Or by we will keep a compass needle. Compass needle north for whichever side it is running, that will be the direction of magnetic field. Or will simply draw magnetic field line. Now that has also come. What does it magnetic field line give? Direction of magnetic field, isn't it? Suppose I draw this magnet. This north pole, this south, this become the magnetic field line. This become the magnetic field line. This become the direction of magnetic field. The magnetic field's direction at this point will be what? Here. The direction of magnetic field at this point, magnetic field line is going like this. Here it is direction of magnetic field. At this point, lines are going like this. Here. So by the magnetic field direction, we have now understood very well. On the field lines, we draw a tangent like straight line like that. The direction of that field at this place will be this. We'll draw like this. Okay. But now the question is, what is magnitude of the magnetic field? What is the value? Where is the field strong? Where is it weak? Now, no formula is given in your syllabus, thankfully. Like the formula for force is ma, displacement, velocity is time. No formula for this is given. Come on, be very thankful, be happy. By one formula is reduced. They have explained you with a concept. Concept says wherever field lines are close, the magnetic field is strong. And where the field lines are far apart, there the magnetic field is weak. This is all which is explained. Field lines closer, more crowded, strong magnetic field. Field lines far, less crowded, weak magnetic field. Come on, you comment. I am giving you a question. Everyone has to comment. I give you 1.1. I give you 1.2. I give you 1.3. Now you tell me, arrange these 1, 2, 3 in the decreasing order of magnetic field. Come on, comment after pausing. Strength of magnet. Strength means the power of the magnetic field. 1, 2, 3. 3 points you have to arrange. Come on, Elsie. Done it. Sure, promise, Markism. Okay, yes. Now look, 1, the field lines look very close. At 2, they are little far apart. And 3, the field lines are very far. Look, here they are very far. At 2, they are still less far. At 1, they are very close. So the strongest magnetic field will be at 1. After this, I'll think will be at 2. And after that, think it will be at 3. So your syllabus will never ask the value of the strength of magnetic field. It won't ask how much magnetic field we measure in Tesla. How much? 5 Tesla, 10 Tesla, 15 Tesla. No. It will always make you compare where it is strong and where it is weak. What concept to use in there? Where the field lines are close, there it is strong. Look here, they are very close. No, what does it become? Let's zoom. Come. Look now carefully. Field lines look close here. Yes. here little far, here they are very become far. So 1 is strongest, the 2, then 3. So you just have to tell using this concept. Is it clear, bhai? Come on, I'm giving you a question for homework. Everyone will comment the answer to it. I'm asking the question, I'm giving you 2 points. 1 point is your A, this one, and 1 point is your B, this one. You tell me out of A and B, where is the field strong? You have to leave in the comment. Out of A and B, where is the field more strong? You have to leave in this comment. Okay. Look at one more concept. Do this in the comment. Okay, bhai, we'll do it where the field is close. For a bar magnet, carefully. Look carefully at the bar magnet. Near the pole, field lines become very close. See? Because everyone has to enter. By all the children went out from the house, went to play, went out, wandering. But door to came back is only this big. So all the field lines will start sticking right here. It will start clinging. So here the field lines become very close. Where? At the pole. Because these are the doors where the field lines has go out from and come in. Right or not? So look, many field lines are came out of here. This remove this door, you comment, okay? I'm removing it from here. Yes. Come on. Now look, all the field lines came out from here. The place is only this much. So what will it become? Close. And all of them have to emerge like this. So beta, there will be a lot of crowding at the poles. At the poles, the field lines are very close. That is why for a bar magnet around the poles, the magnetic field, what will it be, beta? Will be strongest. Will it be or not? Because the field lines are very closest. How are the field lines? How are the field lines? They are extremely crowded. There is a lot of crowd. Jam is there. Say it is understood. And far away. If I go far away, look, I'm going far. What is happening to field line? It is getting further away. So if we go far, how will the magnetic field will become? It will become weak. Because how the field lines become? How have lines become? They have separated. They have gone very far. Isn't it? And when it is exactly at the pole, the field lines are close. So where is the strong magnetic field? At the pole. And it decreases as we go far away. Come on, bhai, let's move forward. This is done. Yes. Uniform and non-uniform magnetic field. Now what is this? Beta, uniform means not uniform. That is one. Uniform means same. If something is the same everywhere, we say it is uniform. It is uniform mixture. It has uniformly inside it. It is uniform means everything is same. Okay. So uniform magnetic field, what? That the magnetic field in that area is same everywhere. The value is also same. The direction is also same. It is equally strong and in the same direction. Field is same everywhere. What is the field everywhere? It is same. How are the field lines? They are parallel field lines. Field lines are at equal distance, meaning if you see such field lines anywhere by field lines can be anything. Just now you saw field line in the magnet. Different types. Here like this, here oh, here like this. Anywhere beta in this world, you see such a field line, which is how? First thing, it is parallel. Second thing, how is it? Equal distance. If this is 1 centimeter, this is 1 centimeter. Then this is 1, this is 1. It is equal distance. If you see such a field line anywhere, what does that mean here? Uniform magnetic field. Meaning. I take 1 point here. I take 1 point here. I take 1 point here. I can say anything 1, 2, 3. So the magnetic field of 1 will be the same as 2's and the same as 3. Whether it is about magnitude or about direction. What will the magnetic field be everywhere? It will be equal. Direction, going this way, going this way, this way. And the magnitude, all this equal. This is called uniform magnetic field. Then come non-uniform magnetic field. The name itself tells. Non-uniform means it will not be the same everywhere. Field is different at different places. The magnitude to and direction of the field can be different and different at places. Somewhere it will be 5, somewhere it will be 10, somewhere it will be 20. And direction can also be different. Field lines are not parallel. How will we know? Just not like this, simple. Other than this, if field lines is seen, whatever it looks like, non-uniform. If anything else is seen other than this, anything straight, parallel lines, equal distance. Parallel lines, equal distance. If anything else is seen there, then how is the magnetic field? Non-uniform. That is different everywhere. Field lines are at unequal distance. Look at this. Look now, if I ask here, it is little uniform. But after this, look, it ran away like this. Meaning what kind of field is this? Non-uniform. The field strength and the field direction are not same everywhere. For example, I ask you a question. Look, one point is I took here. Everyone tell why. Everyone will tell commenting. Come on, bhai, everyone will pause the video and comment. I will give you 2 points. I took 1 point here, 1. 1 point I took here, 2. You tell me where is the field stronger and where is it weak. Think and tell, bhai, is it visible or not? It's visible now. Where is the field more strong and where it is more weak? If I look carefully, mere bhai, then here the field lines are closer and closer. So how will the field at 1, bhai? It will be strong. At 2, the field lines are going further away. How will the field at 2? Weak. So 1 is strong, 2 is weak. Means everywhere it is not the same. So what do we call such a field? Non-uniform magnetic. Okay. Chalo bhai, let's move ahead. The question came in 25, 15, 24, 18, 22. Almost every year. This or a similar question has been asked. It is similar to. By convention, the field lines emerge from the North Pole and merge at the South Pole. Why? Why, bhai? The field lines emerge from North and merge at South. Explain, bhai. So what is there to explain? Say, bhai, you made such a way. You said wherever the free North Pole will run, that would be the field line direction. When free North Pole was kept here, it ran here. When we'll keep the free North Pole here, then it would run here. This is why it's happening. The same is written. Reason. Field lines are drawn along the direction in which North Pole of a compass needle moves. So this is its reason by the North Pole of the compass, because it ran in this direction. This is the direction of field line. That is why it emerges from north and goes to the south. Next. State the relationship between strength of the magnetic field and the degree of closeness of the field lines. The closer the field lines will be, the stronger the magnetic field will. The further it, the lesser the same is written. The closer the magnetic field lines, the stronger the magnetic field. The closer the lines, that much strong magnetic field. Now think, I write a point 1 here and here write 2. Where the field line is strong? At 1, field line is close. Next. The magnetic field line is given region is uniform. Draw a diagram to represent it. Uniform magnetic field, parallel line at equal distance. Clear? Chalo. Magnetic field lines due to a bar magnet. Due to 2 bar magnets. In the NCERT is not exactly given anywhere, but question is asked in the board. Suppose we take 2 bar magnet instead of 1. These are 2 different bar magnets, beta ji. These are not same. Suppose I bought 2 bar magnets. This is one magnet at south pole right here. This is another magnet in north pole somewhere here. These are 2 magnets. Where do magnetic field lines emerge from? From the north. Where did it go? To the south. Emerge from north at 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 south. And anywhere they didn't cross there. These are 2 different magnets. These are 2 magnets, not 1 magnet. Remember it. There are 2 magnets. One is this, one is this. Okay. Suppose there are 2 north poles. 2 north poles are kept nearby. Its south will be somewhere here. Its south, 2 magnets. Its south here. Its south here. Magnetic field line from the north pole. It emerged like this. Emerged from the front to or 2 magnetic field lines cannot cross each other. So bhai, the magnetic field change its direction. Where do magnetic field lines emerge from? Emerge from north, walk from north, walk, emerge from here to walk. But these 2 will clash and 2 magnetic field lines cannot cross. So what do? They said, yaar, we don't like this, we will clash. Do one thing. If it came like this, it would crash. But the line got repelled. What do like poles do? Repel. So the lines also repelled. Repelled, shook. And there are no field lines in the middle here. Similar beta, south poles are kept. In the south pole, magnetic field lines come inside the south pole. So like this, it should come like this and it should come like this. But bhai, if it come like this, it will cross each other. We don't have to cross. So look, it came here like this. Look, it wanted to come like this and go like this. And it would come too, but it would have crossed. So don't draw any field line like this. So what is it doing beta? South repel each other. So the line then far away. Run far, bhai, run far. This is done. So what is it showing beta? That lines are dense between opposite poles. When there are opposite poles, the lines are completely filled in the middle. Meaning what is it showing? Attraction between opposite poles. These lines and the opposite poles are absolutely stuffed, creamed fully. But when they are same poles, there are no lines in the middle. Lines also repelled. These went like this. So what is it showing? Lines are repelling from 2 same poles. Repulsion between same poles. This and this. Is it clear? Come on, look at the question. It come in CBSE term 2. Look at this. Name the poles P, Q, R and S of the magnets in the following figures A and B. There is figure A, there is B. First tell the answer by commenting. Pause and comment, it should be done. Come on. I have to tell the P and Q poles. Field lines are going out from P. They are coming inside Q. It is very easy. P is my north pole, Q is my south pole, it is finished. Let's come to this RS. Now if I look carefully at RS, these two different magnets, field lines are emerging from R, they are coming inside south, emerge from R, coming inside south, sorry, S, emerge from R, goes inside this, emerge from R, goes inside. So R is north pole and S is south pole, but both of them are different magnets. Imagine these are little, this picture, this is the one. Have you seen carefully? This is one. Is it this one? Look, this is R and S, came from here and entered here. See, this is the same thing is made, came from here and entered. So these are two different magnets. So it is done. What is our P? Here we have to write P is our north, Q is our south. Similarly, R is our north and S is our south. Okay, what is next? State the influence drawn about the direction of the magnetic field line. What all you learn? The magnetic field lines emerges from north and go to the south. Inside the magnet, south to north. Can you see this? Inside the magnet, it is north to south. Same things. Learn magnetic field lines always emerge from the north pole, enter the south pole. Inside the magnet, they move from south to north. Magnetic field lines form closed loops. Biot is making. It's went and made a closed loop. What are these two magnets? Don't make mistake in this. These are two different magnets. Chalo bhai, let's move back. Field lines by iron filing. Can we really see the field lines? Yes, we can see. There is iron filing experiment. Iron filings means iron churan. What is this? Iron's beta churan. By grinding, you have made small pieces of iron. There are some impurities of sulfur and carbon too in the iron filings. So you took finely grind iron filings and you put it on the white paper. Okay, what are we doing? I'll tell you. Then you put a bar magnet on it. Then you did on the paper a little. You did like this. You move the paper like this. After shaking the paper, you saw that the iron filings, the chura of the iron is taking a specific shape here. It is becoming something like this. By now, it must have been clear to you that why is it made like this. It's not very shocking thing for you. What is it? Magnetic field lines. What happened? The iron filings were arranged in the field lines. Why? Because wherever is more magnetic field, there see are more iron filings. Where there is more what are in the poles? A very strong magnetic field. Because weapons in the field lines on the poles, they are very close. It is not on the field lines. Sorry. What happens to the field lines on the poles? Very close. See here a lot of iron filings is gathered here. And see further it is becoming less. So according to field lines, according to magnetic field, it is arranged. The same thing is told in the experiment. What are the observations? Iron filings arrange themselves in curved lines around the magnet. What are these curved lines? Magnetic field lines. The lines are dense near the poles and spread out in the middle. How is it here? It is dense. Why is it dense? Because field is more here. Conclusion. Iron filings show magnetic field lines. What are they showing? Magnetic field lines. The field is strongest at the poles. At the poles, most amount of iron is accumulated because their field is strongest here. Outside, it keep decreasing. Clear? See, a question is also came about it. In 2024, 25, 15, 22, in any one of set or another out of many sets, question definitely come. Why do iron filings arrange in a particular pattern? Why do they arrange? Because of magnetic field, right? Themselves along the direction of magnetic field created by because of the magnetic field. It has a particular pattern, right? It's not like it's becoming round, one side these lines, or straight set lines. It has a particular pattern. If we look closely, what is it a pattern of? They are arranging themselves and pattern of the magnetic field lines, aren't they? Look at this pattern, A, this, A, this, A, this, A, this arranging itself, direction of the magnetic field. What does crowning of iron filings at the end of magnet indicate? What does the crowning indicate? The magnetic field is strongest at the poles, right? This what indicates. What do the lines along which the iron filings align represent? These lines along which, what do the lines along which iron filings align represent? What do they show? They show magnetic field lines. Clear? Come on now, let's move forward. Now, bhai, we come to very lovely concept. Till now, everything was understood that there was bar magnet. It had a magnetic field whose direction is found by direction the pole of compass runs towards. Magnetic field line emerges from the north pole. It goes to the south. It was very easy thing. Now, very lovely discovery happened which Mr. Oersted made. So Henry Oersted was scientist. He made a discovery. They say it's accidental, nothing accidental. A centuries of hard work, saab. He observed that if there is a circuit, a wire was coming out of this battery. Obviously, this going through the wire current I. What is going? Current I. He observed that if current is flowing through this circuit, if current is flowing in this circuit, saab, If what is flowing in this circuit, what is flowing, if current is flowing in this circuit, then he observed that if a compass is placed near it, the needle is deflecting. The needle should reflect from a magnet. But if place a magnetic compass near current, the needle deflects. What does this mean? It means that the wire which has current behaves somewhat like a magnet. A current carrying wire creates a magnetic field. What a path breaking discovery happened in science. Yaar, this small piece you were thinking of a toy magnet. This is not a magnet. The wire that has current flowing in it also a magnet. Now this blew minds of the scientists. They said, acha, the magnetism and the electricity, which we were studying differently, are actually one part of science, electromagnetism. Electromagnetism. They said current, which we thought of separately, like electric current that lights a bulb and the fan, and magnet that attack different things. We thought they are separate worlds, both are same world. Why? Because a current carrying wire creates a magnetic field. A compass needle deflects when placed near current carrying wire. Current carrying wire produces magnetic field. If you have wire in your hand, sahab, and you take a magnetic compass near it, it deflects. Meaning this wire is establishing its dominance, magnetic field around itself. What is current creating? Magnetic field. The path breaking discovery was made by Oersted sahab. Now the question comes that if a magnetic field is formed from a wire, then what is its direction? Come on, let's take a science forward. You made a good discovery. You found out that magnetic field is created by current. What is its direction? So now a rule was made to find the direction. What is the rule? That you hold the current carrying wire with your right hand. This right hand which we eat food, the left hand you know what you do with it. You hold the current carrying wire with your right hand. Your thumb, the finger, should be in the direction of the current. After that you close your fingers. The direction in which your fingers close, the direction in which your fingers close is the direction of the magnetic field. This is a current carrying wire. I held it with my hand and right hand. And where is my thumb in the direction of the current? I was looking for a stick but couldn't find. Where is the thumb in the direction of current? The direction in which my fingers curl, rotating like this, rotating. The direction in which my finger curl, this is the direction of magnetic field. I will get some kind of magnetic field like this. What is this, sir? Of a circle. Yes, so what happened? How is the magnetic field? Different at every place. Look here, where I am now. Here. Like this. A circular magnetic field. This rule is for finding the direction of the magnetic field for a current carrying wire. This rule was called Maxwell's right hand thumb rule. Maxwell sahab. Maxwell is a very great scientist in the field of electromagnetism, combining electricity and magnetism. He said that if there is a current carrying wire, to find the magnetic field due to it, place your finger, right hand thumb in the direction of the current. Then wrap your fingers, curl them. The direction in which your fingers is wrapping is the direction of magnetic field. This was explained. Hold a current carrying wire in your right hand. Keep your thumb pointing in the direction of the current. The thumb is the direction of current. The direction in which your fingers wrap, curl around the wire gives the direction of magnetic field line. Maxwell's right hand thumb rule has been asked directly in 25, 22, 20. That is why you should remember this rule. Why is Maxwell's right hand thumb rule used? Why is the right hand thumb rule used? To find the direction of magnetic field produced by current carrying wire. Look, two more examples are given carefully. Come, let's see. This is the current carrying wire. Current is going up. How will the magnetic field be? Took the right hand, held the wire in the hand. Where is the thumb? In the direction of current. Where is the current? Upwards. And curled the fingers. Curl. Close like this. Now look, the finger went this way. So this is magnetic field. Went this way, magnetic field. Here this way, magnetic field. Here this way, magnetic field. And this, how it has become? Circular magnetic field. Look here, current is going downwards. What to do now? Thumb stays up. Thumb can also go down. Are you mad? What are you talking about? Put the thumb down in the direction of the current and curl the fingers. Now look, the magnetic field outside here, on this side, to the right, here towards the back, here towards me, and like this, and this. It is a circular magnetic field. How is the magnetic field? A circular shape. This became the magnetic field. What is this? Maxwell's right hand thumb rule. What did we find from this? The direction of the magnetic field due to the straight wire carrying current. Is it clear, bhai? Come on. We do a lot of practice too. Don't take tension. I'll make you practice quite a lot now. Don't take tension. Let's read a little more. Magnetic field due to, come on, let's make you practice first. You will enjoy it. Here it is. Come, let's practice. Come on. Now a question has come. Let's do this practice first. Find the direction of magnetic field produced at point P. Come. We have to find the direction of the magnetic field at this point P because of the current. We have to use Maxwell's right hand thumb rule. It is asked, how will the magnetic field at point P? Come on, what should we do? This is the wire, current is going this way. What does the rule say? Hold the wire with your right hand, held it. Place the thumb in the direction of the current, placed it. Now curl your fingers, look carefully. Now at point B, where is my finger going? Towards inside. Look in the point B2, where is my finger going? Toward inside. So how is the field be here? Cross. Cross means where did the field go? Towards inside. Wherever I draw cross, it means into the paper, inward. Whenever I indicate cross, you should understand N2 paper, N2 paper, inside. And whenever I draw dot, you should understand out of paper, coming out of the paper. Whenever I draw cross, it means going inside the paper. Carefully, yeah, don't take tension. Look at this wire. Why is current going? I held the wire with my current hand. Okay, sir. Where should the thumb be? In the direction of current. Put it in. Okay, sir. It's good. Let's make your bigger. Come on. This. Yes. Now look. I held this. Where is the thumb? In the direction of current. Okay, sir. Now curl the fingers. Here the magnetic field is this way. Here this way. Here this way. And when I'm coming to this on the paper, this here. Where is my hand going? Look, my hand will rotate like this. Really look, if you truly see the magnetic field somewhat like this, it will be circular. It will be circular like this. But when they asked me the exact magnetic field at some point here, so I made it like, where is it going? Inside. Let's see another example. Slowly you will understand more. Let us see another example. Let's see this one and second one. Now I have to tell the magnetic field at point P. Come on. What should I do first? This one will see very easy. It is where? It held with the right hand. Where will thumb go? It went in the direction of current. Now tell the magnetic field. At P, look here. Outside. If I look at the magnetic field, where will it go? Inside. Where will it go? This side. Toward inside. And when I come here, towards outside. So at P, what is this? Outward. Look at the previous one, you will understand more. Now look at this. I held the wire, right hand thumb this way. At P, magnetic field inside. And if I look here, at this place, look, I held it at P inside and here towards outside. Is it clear? Is it understood? Shall we do more? Is this one clear? I held it right hand. Don't use the left hand, right hand. Current where upwards. Here magnetic field inside and look here outside. Let's see one more. Look at this. Yes, come on. Now this time the current is downwards. Carefully. Come on, comment and tell whatever. Comment first. Current is going downwards. Held it. Where are the fingers going at P? Inside. So here the magnetic field is towards inside. Inside. And here tell at this place. Inside. Where is it coming? Towards outside. Is it clear? Is it understood? Come on, this one is good question. The fifth one. Let's see who will tell this correctly. Now tell, will the magnetic field at P be inside or outside? Comment, it will be inside or outside. Comment at P magnetic field inside or outside. Whoever told by, you are saluted very strongly. Shabash. Come, let's see. Where is the current going? Upwards. I held this with right hand. Now look, here this wire are two wires. 1, 2. Will we get magnetic field at P due to both wires? There is current in this one too. There is current too. Current carrying wire creates magnetic field. I held this thumb upwards. Look at the magnetic field at P. How is it going? Inwards. So due to this, it is inside. Let's say due to this one, current is going upwards. I held it. My thumb upwards. Come on. Here the magnetic field is inside. But on this side, outside. Look, if I hold this with the right hand and keep the thumb upwards, this inside. But when I reach this side, the magnetic field is outside. So bhai, he is saying make the magnetic field inside, he is saying make it outside. The distance from both is equal, meaning both will have equal dominance here. It is at equal distance, equal dominance. So bhai, what will the net magnetic field be here? 0. There will no magnetic field. This one will create magnetic field toward inside. Khachak, khachak, khachak. Go inside, go inside, go inside. And this outside, outside, outside. It is an equal distance from both. So their pressure will also be equal. Net magnetic field will be 0. Understood? Look at this one, the fourth one. Come on, now tell me the P by commenting. How much is it? If you get it right, meaning you got it. You have to tell P and Q also. Let's say 2 points, P and Q. Come on. Then it, current is this way. I place thumb this way. Now I will curl the fingers. Place it. First open the fingers like this. Get ready like this. Then like this. The opening the fingers. Ready like this. Ready? Go. A at Q. Inside. Inwards. A at P. A outside. Outwards. Okay. Place the thumb like this. Got the fingers ready? Ready? Go. A at P. Inwards. A this way. Outwards. Say, is it clear? Very good. Come on. Question. CBSE 2023. The resultant magnetic field at point P situated midway between two parallel wires placed horizontally is carrying a steady current. Tell me here what will be the net magnetic field. Everyone knows how much it will be. This is the one I made here. Do. It will be 0. Bhai look, where will the magnetic field due to A? Place this. Due to A, how is it going? A inwards. So due to A inwards and due to C A P. A outwards. Due to C outwards, due to A inwards, isn't it? Look, due to A at P. We have to tell the point P. A inwards. And due to C, I reach P on A. Look, held it like this. Ready? Here is an inside. But I needed P. I needed at P. I reach P, B reach P, reach P outwards. So it is an equal distance from both. What will the net magnetic field be? 0. There will definitely be an option 0 here. Here is option C, 0. Clearly you got this. Come on, we'll practice again. Let's read it a little bit. A little study is also necessary, beta, not only mischief. Come on, let's understand what does NCERT is telling. Magnetic field due to a current through a straight conductor. Come, let's see. One experiment was done. Same cardboard. What was put on the same cardboard? The same iron powder. Iron powder. A straight current carrying wire passes perpendicular through a white cardboard sheet. A wire was passed through a white cardboard sheet. Okay. Iron filings are spread evenly on the cardboard. What did we put on this? We spread iron filings. Okay, bye. Then we knocked on it. What will happen? The iron filings will arrange themselves. How will they arrange? In the direction of magnetic field. We saw how the arrangement of iron filings happen. We saw that the arrangement happened in a circle manner. Circular, circular, circular. Why circular? Look, if I look carefully at this wire, where is the current going? Downwards, right hand. Here it is, current. Here inside, here outside, here inside, A outside, outside. What is forming around it? Look, A, start from here, come down. What is made? Circle. And not one, many circles, concentric circles. Sir, what is this about concentric circle? This is a wire. By wire concentric circle forming. Look, yes, this is a wire by. Current is going in it. Tell me one thing. If I ask magnetic field here, you will say inside. But if I draw, it will become a circle like this. Okay. When I ask for a magnetic field here, I place my hand. Another circle is formed. If I ask for the magnetic field here, you will place your hand here, say inside there or side here, meaning one more circle will form. So what are the magnetic field lines actually? Concentric circles will keep forming around the wire. Due to a straight current carrying wire, how will the magnetic field line be? One circle, two circle, three circle, four circle. Concentric circles will keep forming around the wire. There will be magnetic field here too. How it will be? Look, the wire is like this magnetic field inside. It will be here too. If I ask you, tell the magnetic field at this place. So you will place your hand and here lift it up like this and draw a circle. This is why, look here, what are the magnetic field lines become? They have become concentric circles. So this thing you should remember. That the magnetic field line that forms due to a straight wire, how does it form? Concentric circle. Bar magnet was different, emerging from north going to south. How does it due to a straight wire? Concentric circle will form. Okay. Same thing is told here. Factors on which magnetic field due to a straight wire depends. Now, bhai, where will the magnetic field more? Where will be less? What are the factors? You can understand this very easy. First you tell me, the further you go from the wire beta G, this is a wire, current carrying wire. The further you go from the wire, what will happen? Its dominance will keep decreasing. So as you go further away, the magnetic field will keep decreasing. So with distance, the magnetic field will decrease. Second thing, the more current you put in the wire, the more the magnetic field will be. The stronger the current is, the more the magnetic field will be. So you have to remember two things. First, the further you go from the wire, magnetic field will be less, dominance will be less. You are getting further. And second, the more current you will put, the more in the magnetic field. The same is written. On what factors it depends? First, current. Current increases. The more the current, the stronger the magnetic field. Distance. The further you will go, weaker magnetic field keep decreasing. Third thing, reverse the direction of current, the direction of magnetic field reverse of the wire. If you will reverse the direction of current, then the direction of magnetic field also will reverse. Look at this. Suppose this is a wire. The current is going in this. Tell me, how is the magnetic field here? Tell me, by inward or outward? I have kept my hand here, right hand, thumb upward. Where is the magnetic field? Inward, sir. How is it coming? Inward, sir. Suppose I reverse the current direction. Let us say I change the direction of current like this. Now tell me what the magnetic field here would be. Sir, how will you calculate it? Change the current direction. Now tell me. The thumb will go like this, definitely. Here the magnetic field is inwards, and upon here coming, see, the thumb went like this. Yes, gone, sir. Here magnetic field inwards, and how it becomes at this place? Is it coming out or not? Outwards. So reversing the direction of current reverses the direction of magnetic field. See this, by. Suppose the current is going like this, and I ask you, how would the magnetic field be here? So I kept the thumb in the direction of the current, right hand like this. Here it would coming on P. It's coming outward. I reverse the direction of the current. I do it like this. Now what would be the magnetic field at P? Kept the thumb, current direction. Look at P. So on reversing the direction of current, direction of magnetic field also reverses. Same is written. Reverse the direction of current, direction of magnetic field reverses. The same thing is written. Field is inversely proportional to distance from wire. The further you go away from wire, what would happen to the field? It would get weaker. Okay. Let's go. 2025, 18, 23, 22. What is the question? Draw the magnetic field lines when current flows from conductor X to Y. The current flow to the conductor X to Y. What do you have to make? Magnetic field lines. You will make it. What would it like, by? The current is going like this. You kept the thumb of the right hand in the direction of the current, fingers curled. How is it? Circle. And one or a lot? A lot. So one circle, two circle, three circle. What it be? Concentrate. Direction have to be made by. So current is going in this direction. So feel like this. So here, this side, here, this side, here, inwards, here, towards outside. Concentric circles have to be made. What is next? Name and state the rule used in determining the direction of magnetic field lines in the situation given above. How did you make this magnetic field line direction? Tell the rule. Which rule is this? Maxwell's right hand thumb rule. So stated by that, hold the current carrying wire in your right hand, keep the thumb in the direction of current, and then where the fingers would curl, that is the direction of magnetic field. Clear? Activity 12.4, current wire placed over compass. Now what did I do? I placed the current carrying wire above the compass. What did the compass used to tell? The direction of magnetic field. Now think a compass kept below it. So where will the compass go? You have to tell this is a wire. Below the wire is a compass. Now you have to tell where compass would run. It would run towards west or east. Comment. One is A and one is B. In both the cases, you have to tell whether the compass will run towards east or west. Let's think about it. I held the wire with my right hand. Compass is under it. Okay. And I kept the thumb in the direction of current. Okay. I'm saying where would the force be applied on the compass? Where is the magnetic field? Here. Where is the back side? Here. Behind it. Behind. This is the wire. Behind it. Behind it, what is the magnetic field? Like this. Where this is the magnetic field? Does the north pole run there? Yes, sir. So will the north pole of this compass run towards the west? Yes, sir. Totally true. So where will the compass north pole run? Towards the west. Now I reverse the direction of the current. Now I have reversed the direction of the current. Now tell, the compass is kept behind. This is a wire, and behind it there is compass. Thumb will go in the direction of current. Where is the current going? Below. So the thumb went in the direction of current, fingers curled, 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 and are coming behind here towards me. Is it or not? See, this is my wire. Can you see it? This, is it visible? Yes. Now I kept the thumb in the direction of current. Now the fingers bend. Where are they coming? Where is the back side? Compass is behind it. Where is it going behind it? Here, towards me. Will the north pole come this side? In the east. On reversing the direction of current, direction of the magnetic field also reverses. This diagram shown somewhat like this in NCERT. Don't get confused, don't be scared. It is similar diagram. It is nothing different. This is the current going. This is the current and this is the compass placed. Where is the compass? It is placed behind the wire. Wire is placed over the compass, above the compass. Keep that in mind. Yes. Now current is going like this, like this. Can you see this? Current is going like this, upward like this. Now look, how will the magnetic field be downwards? The compass is below it. Like this. Kachak, kachak, kachak. So the north pole ran this side. This is the same thing shown in the second diagram too. The direction of the current has been changed. Where is the current going? It is going downwards in this. The compass is placed below it. If we go down, the magnetic field kachak, 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 kachak. So north came here. Is it clear? Why are you teaching this, sir? Because it was an activity and question has come on it. It came in 2025. It came in 2013, 2022. What does the circuit diagram show? What is the circuit diagram showing you? This circuit diagram showing us that when a current carrying wire placed over a magnetic compass, the magnetic compass shows deflection. This happens because the current carrying wire produces a magnetic field. This is written. This diagram shows a current carrying wire placed over a magnetic compass. It is placed over it. The compass deflects when current flows in the wire. This shows that a current carrying wire produces a magnetic field. Why is the compass deflecting? Because what does a current carrying wire produce? A magnetic field. Next, what will happen if the direction of current is reversed? Reverse the direction of current. So what will happen? The direction of magnetic field will reverse. The direction of deflection will also reverse. Look here. Here current was going up. So the north pole ran to the west. Current went down. North pole ran to the east. Look, current went down. Where did the north pole went? In the direction of east. It ran this way towards east. So they are asking this, what will happen if I reverse it? Then if a circuit diagram is drawn, then draw that. You have seen it. The direction of deflection of compass needle will also reverse on reversing direction of current. Why is that? Because the direction of magnetic field reversed. Come on. Now magnetic field due to a circular current carrying loop. Until now we had straight wire in which current was flowing. Now I bent the same straight wire into a circle and made a circular loop. Now it has become a circular loop. Current is rotating like this, round, 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 round. How will the magnetic field be due to this current? Come on. I take a point at the center. At the circle center, I took point O. Here you have to tell the magnetic field due to this current at this point. Pause and comment how it will be. I will take my right hand, place the thumb in the direction of the current. I need the magnetic field at O. I am curling the fingers. At O, it is going inside. Like this. Will there be magnetic field line like this? Like this. Kachak, kachak. Going inside. So I draw a cross here. Tell the magnetic field due to this. Current is going up. Place the thumb in the direction of current. Place the thumb current direction. Curl the finger. I have to see that O. Kachak, kachak, kachak. Where is it going? Towards inside. Like this. From outside to inside. Magnetic field from outside to inside like this. Kachak. Look here. Current is going down. Place the thumb in the direction of current. Curl the fingers from outside. Inside. Inside. Like this. Okay. Look at the upper current. Current is going like this. Place the thumb in the current direction. Magnetic field. Kachak. Kachak. Meaning I saw that due to this current, the magnetic field due to here kachak. Inside due to this kachak inside, due to this you kachak inside, because of that also inside. Meaning the magnetic field is going inside like this. It is entering towards inside from here. Okay, it is very easy. Imagine if I look at the same loop from when? From this side the field is even entering inside like this. Because of this like this. Because of this like this. Because of this like this. Going inside. If I look at the same thing from behind this smart board, so will I see the field line coming outside? My side, from here gone inside, from there came out, from here gone inside, from there outside. Meaning if I look from behind, I will see it coming out. If I look from here, I see the field going inside. Okay. Acha. NCERT gives you this diagram. How to make it? Let's think. I held this same loop, held it and made it like straight like this. How will this diagram come in NCERT? I held the same loop like this and held it and made it straight like this. Now tell me, how will the field line be? Going inside from here, outside from there. Going inside from here, there outside. When I make it like this, from this side inside, from there outside, from here inside, that side outside. How is the field line here? Kachak, kachak. Going inside from here, outside from that side, like this. When I make it like this, the field line will enter from this side and exit from that side. I held this and by holding it, I made this. Now look, the field line entered from this side, exit from that side, entered from this side, exit from that side. This is field line due to circular loop. Hold this loop and put it horizontally like this. Oersted one made it like this. Field line entered this, from there exit. Okay. Look carefully, it looks a bit like a bar magnet. The field line is entering from one side, exiting from one side. In a bar magnet, the side where the field line enters is which pole? South pole. The side where it exits from is which pole? North. Here too, it looks like the field line is entering from one face. What did it become? South. The field line is exiting from one face. What did it become? North. Simple method for its magnetic field line is that field line will enter from one side, it will exit from one side. Is it clear? If I reverse the direction of the current in this, magnetic field line will become exactly opposite. Then enters from there and exit there. I will show you height. Is it clear now? Is this understood? It is a circular loop. Place the thumb in the current direction here. A kachak. What is happening inside the loop? Place the thumb in the current direction here. A kachak inside. So it is entering inside like this from all sides, like this. And it must be exiting from that side. When I make this straight, it is entering inside from this side and exiting from that side. Now I said you field line entering from inside, exiting from that side. It's like a bar magnet. Field line enters south, it exits from north. So it looks similar. Okay. Now for example, suppose I took it like this. Now I place the same loop like this, horizontally like this. Now current is flowing like this. Now tell me, where is the field line enter and where will it exit? From top to bottom or bottom to top? Think enter. Current is flowing like this. You don't have to do anything better. Place the thumb in the direction of current. Okay. Now tell the field line, kachak, from top to bottom. Place the thumb in the current direction. How is it current flowing? It is understood like this, like this. Clockwise. If you look from above, in the direction of the clock, like this. In the direction of clock, in the right hand current is flowing. So I showed the current at this place, this outside, here, at this place. Place the thumb in the current direction, field line there, kachak, meaning from top to bottom. So field lines will enter from top, exit from the bottom. The side from which the field line entering, what will it become? South. The side of exiting, what will it become? North. Suppose I reverse the current. How was the current looking from above? Round, 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 round. If I look at from above. So how is current looking? This, rotating in right hand, means rotating clockwise. How is it? In the clock direction. If I flip the current, reverse it, this is anti-clockwise. Look from the above this time. It is placed horizontally like this. Anti-clockwise, isn't it? Current is rotating opposite. Now tell me. Place the thumb in the direction of current like this. Field lines from bottom to top. Field lines from bottom to top. Meaning the field line will enter from here and from here. Sorry. The field line will enter from here and exit from here. The side from which it enters will be south and the side which it exits, north pole. Okay. How was this looking when seen from the above? It was anti-clockwise. Seen from above, how was the current looking? Anti-clockwise. You saw that I flipped the direction of the current. I changed it from clockwise to anti-clockwise. So the direction of the field also reverse. It reverse, which is also the correct thing. Now remember the trick to remember this. Scan. What? The side where you see the current as clockwise. C means clockwise. There will form your south pole. The side from where you see the current as anti-clockwise, anti-CW. There will form north pole. Finished. Simple. Now look at this. How does it look from above? It looks clockwise. Which pole on the top? South. Look at this. How does it look from above? It looks anti-clockwise. Which pole on the top? North. Scan. South clockwise, anti-clockwise, north pole. Clear? Now come on, tell me quickly. I gave it to 1, 2. Everyone will pause and comment A, B. Tell me current towards you. Sorry, which pole will form towards you? In A, current is like this. in one current is like this. Tell me which pole is towards your side in both. Quickly. What kind of current is this looking like? It looks clockwise. So which pole will this be? It will be south pole. What kind of current is looking like this? It looks anti-clockwise. Anti-clockwise. ACW. Opposite to the clock. Rotating on the left hand. Which pole is it be? North pole. Is it clear? You will catch it now? Very good. Come on. Look at one more thing which CBSE also asked. See, if 1 ton made a magnetic field of 10, then how much will 2 make? They will make 20. 3 tons will make 30. Same thing is written here. If the wire is coiled in many turns and turns are put, then the magnetic field too would be n times by if 1 coil making 10, then how much will make 2? 3, 30, 4, 40. So n times the magnetic field will increase. If wire is coiled in many turns, n turns, the total magnetic field also becomes n times stronger than the single loop. From one single loop, n times more, it will be bigger. Why this happen? This happens because the current in each circular term has the same direction and the magnetic field due to each turn adds up. By because of 1 it was 10, because of 2 it become 20, because of 3 30. What is happening? It is adding up. If n number of turns are put in any coil, because of 110, because of 20, because of 330, the magnetic field will increase in n times. The same thing is written here. Let's move forward. This is understood. A question has come in CBSE 2023. They have asked which option is correct among them of magnetic field line. It's very easy. The magnetic field line are entering from here. It is called north. It has become wrong. From where it enters, that is south. See here. From this side, it is entering south. It's coming out. It's north. Correct. Here, let's say below 2. From here, it's entering north. It has become wrong. See this one. It is entering from here south. From here, it's going out north. Correct. Let's say here below. From here, it's entering south. From here, it is going out north. Correct. So this is completely correct. Right? This one is not met correctly. Clear? Chalo. Next has come magnetic field lines due to a solenoid. Now what is solenoid, beta? Have you seen a spring? Spring. Yes. So if you have a wire in the form of a spring, like this, you call it. This called solenoid. Simple. You give a wire in the shape of a spring. So this is called a solenoid. In this, there's 1, 2. What is there in a spring? 1, 2, 3, 4. A lot of circular turns are there. So this is called solenoid. The same thing is written. A coil of many circular turns of insulated copper wire. The wire that we use, how was it? Of copper. You can take any conducting wire. Insulated means there is plastic layer on it. Now coil of many circular turns. In this, there are a lot of circular turns. Wrapped closely. You have to wrap it very close. In the shape of cylinder is called a solenoid. See, does it look like a cylinder? It's hollow inside. You took a wire like this. What it will like? It would be little light. Have you seen the spring? A little tight. So like that, you coiled that wire in the shape of a cylinder. This is called a solenoid. Now tell me what would be the solenoid's magnetic field? Let's think a little. Beta, this was a coil. How was the magnetic field? It was entering from here, getting out from here. It was entering south. It was coming out inside. We called it north. Think I put another coil in front of it. What will happen? It would enter from here, get out from here. I put one more in from here, out from here. So similarly, I have put a lot of coil. As many as turn would be there are n turns here, n turns instead of 1. So the magnetic field 2 is n time more. So what happens with solenoid is that it gets a very strong magnetic field. By one circular coil, suppose this is circular coil, it was giving a magnetic field. It entered from here, got out from here. Suppose it was 10 magnetic field. If I put n like this, put 10 like this, then how much magnetic field would be? If I put 10, then it would be 100. So it increased the magnetic field of a circular coil. A lot of circulars are put very close like this. So how would it be? How would be the magnetic field lines be? From here it entered, from here it got out, then inside it there out here, then inside it out here, like this it would get out, like this. From here it will enter. What would we call that pole? South pole. From where it get out, what we call it? North pole. So solenoid also had 2 poles, south and north. Clear? So these things you will see here. See this magnetic field lines due to a solenoid is similar to those of a bar magnet. Exactly like bar magnet. Exactly. The magnetic field lines are made exactly like magnetic bar. They are little different. How is it exactly bar magnet? Let's see. Here it is. This is a solenoid. What is a solenoid, beta? A coil of many turns of an insulated copper wire wrapped closely in the shape of a cylinder, a coil of many circular turns. Okay. By that circular coil, from one side the field enters, exit from other. Now here exit from this. By it entered here, this south, this is north. So entered here south, north, north. What it become in the end? North. And what would the first one become? South. So actually it would become two poles, one south pole, one north pole. Like there was one coil. One coil entered from here, it is south. From here north was made. Now multiple are made, so here is south pole, and then it become the north pole. Okay. See the magnetic field lines. They are coming out of north and entering in the south, exiting from north and entering from south. Is it giving you the bar magnet like feeling? Definitely, sir, it is giving the bar magnetic field. It's totally giving the bar magnetic field. Look at the inside. What are the field like? South to north. What are the outside? North to south. This is exactly like the bar magnet. So this makes the bar magnet field lines. If I talk about the direction of its field lines, how are they looking from the outside? Exiting from north, going to south. If I talk about inside, then what do they look like from inside? From south, it would go to north. One important point, very important point. The next one that has come, this is very important. What? That inside the solenoid, the magnetic field lines, look carefully, are these straight lines? Are these parallel lines? Does parallel line meaning is uniform magnetic field? Inside the solenoid, magnetic field is same everywhere. Inside, not outside. Inside the solenoid, the magnetic field is same everywhere. The same is written. Field lines inside the solenoid, what are they like? Parallel straight lines, visible. Parallel straight lines. It means uniform magnetic field. It means magnetic field is the same all points inside the solenoid. How are the lines? Parallel straight lines, equidistant. They are that equal distance. It means if I take any point here inside the solenoid, if I take any points inside the solenoid, I take point 1, I take point 2, I take point 3. Whatever point I take inside the magnetic field will be equal everywhere. It won't be outside, but inside everywhere it would be the same. Is it clear? One more point is written. Its polarity can be reversed. This is a very important thing. You have a normal magnet. You can't change its polarity. Because here whole of the game is of current. You seize the current, the magnetic power is over. What is the name of chapter? Magnetic effects of current. If there is current, then will be magnetic field. You stop the current, magnetic field is over. Okay. If I reverse the direction of current, see the current is going like this. If I reverse the direction of current, then what will happen? You just saw in the circular coil that as soon as the direction of the current was reversed, did you see this? That as soon as you reverse the current direction, what happened to the polarity? It got reversed. When it was clockwise south, anti-clockwise north. So yaar, what is special power of solenoid? You can change its polarity. This thing is not there in bar magnet. You reverse the current, the same is written. Its polarity can be reversed by reversing current direction. The thing that can't happen in a bar magnet. Okay. It is understood by. Now see this a little. I'll give you a question on its basis. That will be homework. Understand the concept carefully. And you will find very wrong solutions on the internet. Understand carefully. I'll give you 2 to 3 points in the solenoid. I'll give you a point number. I gave you a point number 1. It's here. 1 I gave you point number 2. It's here. 1 I gave you point number 3. It's here. I give you point number 4. It's here. You tell me this. What will be the strength of magnetic fields? You tell me about strength of the magnetic fields. Tell me its decreasing order. Where is the most? Where is it lesser? Where is it lesser than that? Strength of magnetic field, decreasing order. Okay. First thing. Point number 1 and point number 2 are inside the solenoid. Inside the solenoid, everywhere the field is same. It means field of 1 would be equal to 2. 1 and 2 both are inside point. What would be inside? It would be equal. Now, how do we compare this? Think. Better did you study the concept? Where the field lines are less, where the closeness of the field lines is less, there the strength of field is less. Relative closeness, did you study? Where there is crowding, the field is very strong. Okay, there's a lot of crowding. Field lines are very close. Can you see? Zoom please. See, here is a very close. Going here, the field lines are getting little further. Is it getting or isn't? A little. What is happening to field lines? They are getting further. Take this point more clearly. Here we take it. Go and see what is happening to the field lines. They are getting further. If they are getting further, then there what will be strength of field beta? It would be decrease. And see at the 4, here the lines are not visible. Here it would be least. So what would be the order? On 1 and 2 it would be most and it would be equal because it is inside. Upon going to the 3, what happened? Field lines got further. So on 3 it would be lesser than that. And on 4 it would be least because on 4 field lines are not even visible. It is very simple. Whenever they ask you the strength of the magnetic field, then what do you look at? How close are field lines. Here it is closest, strongest. Here it become far, here very far. Based on this, there was CBSE 2023 question. A, B, C are 3 points. You have to tell where the strength is maximum and where it is minimum. Don't search on internet, answer is wrong there. Come on, you have to tell by comment and I will tell you the names of the people who comment correctly at the end of next lecture. Come on. Next, strength of magnetic field due to a solenoid. Now, bhai, the magnetic field of solenoid, can we increase it? Can you increase the magnetic field of bar magnet? Can you increase its power? No. Once a magnet in your hand, some magnet feel very big, some magnets papa bring feel like very strong magnet. Some stick to the fridge tightly, some loosely. You can't change its strength. You can change this one because it's man-made magnet. So what does its strength depend on? Catch the formula. B is equals to K N to N N to I. B magnetic field, K constant, catch this. The more the current, the more the magnetic field by its magnetic effect of current. The heavier the current you flow, the more the magnetic field. Second thing, number of turns. The more turns you make, we just studied it, the magnetic field will become n times. The more turns there are, every coil will creating magnetic field, it will increase by n times. The more the number of turns, the more magnetic field. The more the current, the more the magnetic field. This is what written. Number of turns, larger the number of turns, stronger the magnetic field. Current, larger the current, stronger the magnetic field. The more turns are there, beta, the magnetic field will keep adding up. Listen carefully to the third point. It's not usually found in books. Length of air gap. What are these things? Bhai, the more he reduces the air gap, bhai, is visible here. There is air gap between that. There is, haven't you seen string? It has air gap in it. The more that reduces the air gap, how will you reduce it? By increasing the number of turns. Bhai will keep increasing the number of turns tightly, they will come closer. So the less the air gap is, the more the number of turns have to be. And the more the number of turns are, the more the magnetic field will be. This is written, lesser gap, more turns, more magnetic field. Leave the fourth point, this is not correct. They will explain it later. Nature of core. Core is coming up next. Is solenoid clear? Come on, let's explain now. Electromagnet. The solenoid you saw, what was it? Sir, it was spring like this. This is wire. I made it a coil of many circular turns, right? Now if I do one thing in the middle of this, I'm getting some magnetic field from this. I must be getting some, let us say I'm getting a magnetic field from this. Let us say 20. Tesla is the unit, I'm not writing it. 20. Suppose I put some beautiful thing in the middle of the coil which increases the magnetic field, then it will be fun. So I did one thing, I put an iron in the middle of it, a special kind of iron, soft iron. I inserted soft iron in the middle of it. Now soft iron is so lovely, beta, it has a property that it's not a magnet, but as soon as it gets current, this material becomes magnet. Current comes and wake up, it's sweeping magnetic power, wake up. As soon as it gets current, this soft iron will also become a magnet. Due to this soft iron, suppose a magnetic field is created, let us say 50. Now beta, what will the total magnetic field will be? It will be 70. So the way to increase the net magnetic field is electromagnet. Electromagnet is nothing, absolutely nothing. Inside a soft iron core, inside a solenoid. When the soft iron core inserted inside the solenoid, what the soft iron core put in, they say it's core. Core means that is inside. We call this electromagnet. This is electromagnet. So this is what explained here, electromagnet. A long coil of insulated wire wrapped around a soft iron core forms an electromagnet. A long coil of insulated wire, it wrapped around soft iron core. What kind of magnet is electromagnet? It is temporary. As long as there is current, there will be magnetic power. As soon as the current is switched off, listen to the soft iron core, listen to the matter of the iron core. As soon as the current is off, its magnetic power is gone. The current brings the power. As soon as the current stops, its magnetic power also ends. So this is written. How is it? It's temporary magnet. Current magnetizes soft iron core temporarily. This current gives it magnetic power for a little while. Its polarity can be reversed. Every charge the direction of current, the polarity will reverse. Strength of an electromagnet, the story is the same. In the strength of electromagnet, B is equals to K and I. Same points here too. Increase the number of turns, increase the current or reduce the air gap. If you increase the number of turns, the magnetic field will increase. If you make the current higher, the magnetic field will increase. If you reduce the length of air gap, the number of turns will also increase, the magnetic field will increase. Okay, is it clear? Look, in the previous one, extra point is written in the solenoid point. This nature of core. Now if you put a core inside the solenoid will not even survive. So this point is not relevant anyway. As soon as core inside the solenoid, what did it become? It becomes an electromagnet. There are some difference between bar magnet, solenoid and electromagnet. First, there is definition that by what is a bar magnet? It is permanent magnet, fixed poles. What is this? Coil of circular coils of many turns. What is this? A solenoid with a soft iron core. Inside the solenoid, we put soft iron core. Source of magnetism. What is of it? Nature by. Nature gives it to the bar magnet. What is there of it? Electricity. Why? It's got from electric current. What is of it? Electric current of electromagnet. Let's talk about magnetic field. How is it? It's permanent and fixed. Whatever magnetic field is for bar magnet, it is the same. You can change its magnetic field. If you increase the current, the magnetic field will increase. Decrease the current, magnetic field will decrease. Temporary exists only when current flows. This is too temporary but stronger than solenoid. Why is it stronger? Because soft iron core will also give it a magnetic field. If we talk about polarity, what is its polarity? It is fixed. North will remain north, south will remain south. You can change its polarity, reverse the direction of current. Can be reversed by changing current direction of as well. Can be reversed by changing current direction. Okay. Question CBSE 24. The current carrying device which produces a magnetic field similar to that of a bar magnet, electromagnet, and solenoid, not set conductor, not circular loop, not circular coil, solenoid is correct. The magnetic field inside a long straight current carrying solenoid. Tell me, inside a long straight current carrying solenoid, inside, what is it beta of a magnetic field inside? Is very high and the same everywhere. It is not zero, it does not increase, it does not decrease, is same at all points. Okay. Next topic is arrive force on a current carrying wire placed in a magnetic field. Now the story moved a little forward. We know this, that if this is a current carrying wire, let's assume what is this? Current carrying wire, current is flowing in it. Okay, sir. If current is flowing in this beta G, then will it create a magnetic field around itself? What does a current carrying wire create? Magnetic field. What is a current carrying wire? It is a magnet. Current is also a magnet, magnetic field around it. So how does a current carrying wire behave? Like a magnet, isn't it? Okay. If you bring another magnet near this magnet, then both will happen. Either there will be attraction or there will be repulsion. Is it or not? By what is current carrying wire making around itself? Magnetic field. Who makes the magnetic field? A magnet. So it means current carrying wire is a magnet. If we bring another magnet near it, then either it will attract it or repel it. Two magnets either attract or repel. It means this magnet on it somewhat exerting some force, either of attraction or repulsion. This topic is called force on current carrying conductor placed in a magnetic field. If you bring a current carrying conductor in the field of a magnet, then what would be exerted on it? Force would be exerted because this is a magnet and these two magnets will either attract or repel. In this magnet's field, you bought another magnet. By look at this now as if it's iron. Think of it as an iron. Just like iron. If you bring iron near magnet, will force apply or not? It will apply. So what is it by? It is a magnet, right? Not even iron, but a magnet. And if it is magnet, what would be applied on it? Force. What it will cause on same topic? Force on current carrying conductor placed in a magnetic field. What was observed? When a current carrying conductor means take a wire, is placed in a magnetic field, a force is exerted on the conductor which can make the conductor move. Now this conductor can move. If current is flowing in a wire, you have a wire nearby, the current is flowing in it, and now large magnet, not a small, a large magnet, and place it near it. The wire will start running quickly. The wire will start. Why? Because what applied on the wire? Force. The wires in your house that have current, bring a large magnet near them. Generally they are fixed, like them like that. Make it free. Place it somewhere that it can move. Place it on a table, place it on a smooth surface, and bring a large magnet nearby. The wire will start moving. Why? Because the wire itself is magnet. A magnet came here by force is applied. So this is what I'm telling. When a current carrying conductor is placed in a magnetic field, a force is exerted on the conductor. Hey, don't be convinced conductor. It is, I'm talking about wire, which can make the conductor move. This diagram is NCRT, so I bought it. Here they placed a horseshoe magnet. What did they put in middle? A magnet in the shape of a horseshoe. In the shape of horseshoe. And what did they put in middle? They showed a conductor. So force will apply. Now, how much force is applied? This is not in your syllabus. You haven't told how much force. You have told the direction of the force. Which way will the magnet run? Which way will the magnet run? So, to give the direction of force, another rule came, Fleming's left-hand rule for the direction of force. When a current carrying wire is near a magnet, what will be applied on it? Force. And which direction will the force be applied by? What will be known by this rule? Fleming's left-hand rule. What do we do? You have to take out left hand. Children face a lot of difficulty in this. We will tell a shortcut. You have to take out the left hand and make your thumb, your forefinger and your middle finger and make these three mutually perpendicular. How will you do it? Look, these are automatically perpendicular. These two are already visible at 90 degree. Is it visible 90 degree? This becomes the thumb. This is forefinger, middle finger. Bend the middle finger like this. All three are at 90 degree. Then all three. This is at 90 degree with this. This is at 90 degree with this. This is at 90 degree with this. Mutually perpendicular like this. This. First make again. There are 5 fingers. Close it. Thumb, forefinger, middle finger. Is a gun formed like this? Yes, gun is formed. Now take this finger and straighten like this. Now look, all three are perpendicular. This is perpendicular to this at 90 degree. Is it visible? Yes, sir. It's absolutely clear. Is it visible or not? This. Visible or not? Yes. This is perpendicular to this. This is perpendicular to this. Yes, sir. Absolutely correct. And this is also perpendicular to this. All three are what? Mutually perpendicular. First open it as mutually perpendicular like this. Done. Now listen carefully. Now write F on your thumb. Write B on the first finger. Write I on the middle finger. FBI. It's an American agency, right? USA. FBI. FBI. F on this. B on this. I on this. Simple. Now listen. First place this finger in the direction of the magnetic field. B means magnetic field. F, B, I. If this finger is in the direction of magnetic field and the middle finger is in the direction of the current, then thumb will automatically give the direction of force, showing which way the force. Master, I will teach you how to do it. Let's read it. So why we use Fleming left thumb rule? Remember this. Why do we use it? To find the force on a current carrying wire that is placed in a magnetic field. According to Fleming's left hand rule, stretch your left hand. You left hand time, not right. This is right. Left hand. So that your thumb, forefinger and middle finger are at right angle to each other. On what should be all three? At right angle. Look at it like this. Place it like this. Lift it like this. All three fingers are placed like this. Just lift the middle finger up like this. You do all this way, all dirty things. Yeah. Point your forefinger in the direction of magnetic field. Forefinger. F. Look, what is the thumb? F. What is this? Forefinger. B. Middle finger. I. FBI. In which direction should this way place in the forefinger in the direction of magnetic field? Point your forefinger in the direction of magnetic field. This is the direction of magnetic field. Point your middle finger in the direction of current. Middle finger in which direction? In the direction of current. Then your thumb will show the direction of the force to the wire. What will the thumb automatically show? F. Meaning direction of force. So remember this way by. What will the thumb automatically show? Direction of force. Don't align the thumb by, it will align by itself. What should you show with the forefinger? Magnetic field. What should you show with the middle finger? Current. Off. You have to remember this by. The law asked many times. So stretch the thumb, forefinger and middle finger of your left hand so that they are mutually perpendicular. Point your forefinger in the direction of magnetic field. Point your middle finger in the direction of current. Then your thumb points in the direction of force. Come, let's practice question only that will come. It won't like this. Come on, practice. Come on, bye. This is the magnetic field. Here is the magnetic field like this. Going this way. Current going upwards. You have to find the direction of force. Come on, bye. Let's do it. Make the left hand mutually perpendicular. Okay. First set the straight. Forefinger in the direction of the magnetic field. Done. Where is the forefinger? In the direction of magnetic field. Now, set the middle finger in the direction of the current. How do it? Sir, current is up. Do it like this. No, don't change this. This is stacked. Now this can move like this. The finger can move. The finger should not move like this. So the forefinger is the direction of your magnetic field. The middle finger should be current. Where is current? Upwards. How do I take it? How do I take it? Do it like this. Where did the forefinger go? In the direction of magnetic field. Where did the middle finger go? In the direction of current. What will the thumb be showing? Direction of force. Where is the thumb going? Where is the thumb going? Where is it going? Inside. Kachak, kachak, kachak. Meaning in which direction is the force being applied? Towards inside. Where is the force being applied? Into the paper. Inside. Where will the wire go? Into the paper. It will go into the board. Said it is understood. Let's do the second one. Come. Current is going like this. Magnetic field is upwards. Where is the magnetic field? It is upwards. Come on. Pause by yourself. Come on, try it. Pause and comment the direction of force time. Come on. First the forefinger. First the magnetic field will be set. Forefinger. Where is the magnetic field? The air. Which is this? Air. Where is current? Itself. Middle finger where? In the direction of current set. Force from the thumb. Where is the thumb coming? It is coming out. It means this wire will come out like this. Where would the force be exerted on the wire? Outwards. See. Forefinger, magnetic field. Where is it? Upwards. Middle finger, current. Where is it? Here. Where is the thumb? Outwards. So where is the ball will run? Outwards it will run. It means where would the force be exerted? Out of the plane of the paper. Say yes or no. Where would the force be exerted? Out of the plane of the paper. Outward you can call it, simple. Force would be exerted like this. Outward, it means outside of the page. See the next. Now yaar, something is changed here. It is showing magnetic field this side and electron is running upwards. This isn't given. It does this many times. Beta, we have studied in the current electricity. The direction of current is opposite to the direction of the flow of electrons. If the electron is running upwards, then you on your own, where would you assume the current? Downwards. Sometime it won't give you the current. When it won't give, then you have to assume. If the electron is going upwards, mere bhai, if the electron is going upward, then which direction will the current be in? Downwards. So I'll make it current downwards. Direction of the current is opposite to the flow of electron. Chalo, let's start. First of all, what would be the set by forefinger? Magnetic field. Where is the magnetic field? Here, it's set. Current with the middle finger. Where is current? Downwards. It's set on its own. Is the invisible? Visible? Where is the thumb coming? It's coming out of the plane. Should I pull it little in the middle? Yes. First of all, the magnetic field with the forefinger. Where is the current going with the middle finger? Downwards. Where is the thumb coming? Outwards. It means where would the force be exerted? Outward. So should I make the force like this? Hey. How is it being exerted? Outward. Outward. Out of the plane. This wire outwards. It will give you electrons sometimes. Whenever it gives you electron, then assume the direction of current opposite of it. Similarly, they sometimes give you alpha particle, beta particle, gamma. Beta alpha is a positive charge particle. When it gives you a positive charge particle, then the current would be in the same direction. Wherever the positive charge particle goes, direction of the current is the same. Okay. Current is the direction of flow of, rate of flow of positive charge. Beta is electron. It's nothing but electron. It's negative charge. If a beta particle is given to you, then the direction of current will be opposite of it. On gamma beta, no charge. There is no charge. So here no current would be found. See here. Now P plus. What is P plus? Proton. Anyways, plus is written. Whenever there is plus, don't take tension. It means positive charge. Sometimes instead of current, it would make the charge flow. Like here it make the electron flow and there it made the proton flow. P plus proton. Wherever the positive charge goes, there goes the current. So positive charge is going downwards. The current would also go downwards. Simple. Current's direction is the direction of the positive charge. If the charge is negative, then the current direction is the opposite of it. Like beta is negative. So current will flow opposite of it. Chalo. Here tell me the direction of force. The same. Open. With the forefinger magnetic field on this side. Where is the current? Downwards. Middle finger. And the direction of the current. Where is the thumb coming? Outwards. So where would the force be exerted? Outwards. Tell, is the clean? Sir, it's the same. So yes, see the current direction is the same. The positive charge goes here, the current here. Here the negative charge goes, current opposite. Tell me it's clean. Chal bhai. This Fleming left hand rule here, there is a lot of problem in this. Forefinger in the direction of the magnetic field, then keep in the direction of current, then keep the hand like this, do this. It would break. See, anyway, Fleming's left hand rule is used by noob kids. Masters train sigma kuddu kudya will use right hand palm method. There's no tension. It would be very easy. Right hand palm. Open the right hand like this. Open the palm like this. First of all, set the fingers in the direction of the magnetic field. Set the thumb in the direction of the thumb. This palm outside. It would give the direction of the force. Over. No moving fingers like this. Nothing. Simple. Open the right hand palm like this. Open. Where will the fingers go first of all? Towards the magnetic field. Put the thumb in the direction of current. Where the palm is, that is the direction of the force. Okay, let's try. Let's do the same question which we just did. Chalo, come. Let's see this one. Okay, bye. First of all, open the palm of the right hand. First of all, where would the fingers go? In the direction of magnetic field. Is the magnetic field on this side? Yes, fingers went. Thumb would go in the direction of the current. Is the current upwards? Is the thumb in the right direction? Yes. From the palm, we'll get the force direction. Where is the palm going? Inwards. Where would the force? Into the paper. Is it that easy? Yes. Don't tell anyone. Do it silently. The examiner is not coming to check you how you solve. He's not checking copy. Look here. Open the palm, right hand palm. Force on current carrying conductor plays in magnetic field. Open the right hand palm. First of all, fingers, magnetic field. Where is the magnetic field? Made it upwards like this. Take it. Magnetic field upward. Thumb in which direction? Current. Where is the current? Sir, it's there. What to do? What to do? Done. Fingers where? In the magnetic field. Thumb where? In the direction of current. Palm where is it? Out. Where will the force be? Out of the plane of paper. Look at this. Electron is going up. So where the current be? Down. Opposite to the flow of electron. Come on. First open the palm. Right hand palm. Fingers where? Magnetic field. Here it is. Thumb is going up. But where is the current? Down. What to do? What to do? The thumb has to be down. Fingers, magnetic field should not change. This magnetic field, take it by the distance. Fingers in the direction of magnetic field. Thumb in the direction of current. Palm is coming where? Out. Where is force? Outward. Finished. Proton, positive charge is going down. So current will also go down. Open the right hand palm. Finger, first of all, in the direction of magnetic field. Thumb is going up. Current is down. So flipped it. Take. Current also down. Thumb also down. Force from this palm is coming where? Out. Force where? Outward. Halwa methods. Finished, brother. Did you understand? Very good. Good. Now look, factors on which force on a current wire depends. On which all factors does it depend? So beta, this force, its formula is not in your syllabus. You memorize it. I, B, L. Right. You can memorize it like this. Will. B, I, L. Simple. So this force depends on what all? The more the magnetic field will be, the more the force. The more the current in the wire, the more the force. The more the length of wire, the more the force. This is what is written. Look, I, B, L. Will. I, B, L. The more the current will be, the more force will be. The more the magnetic field will be, the more the force will be. The stronger the field you place it in, the more the force. Length of wire, the longer the wire you take, the more the force will be. Will. B-I-L. Third point written is angle. It is very important. CBSE also asks question. Pay attention. From the magnetic field, assume this is the magnetic field in this direction and the wire is placed like this. Does the wire look it as a 90 degree to the magnetic field? Absolutely it does. Wire is going like this, magnetic field is like this. In your syllabus, 99% of question will come like this, where the wire will be perpendicular to the magnetic field. In this case, the force that is applied is the maximum force. Maximum force is applied when the wire is placed at 90 degree with respect to the magnetic field. If I place the wire like this and magnetic field here, magnetic field is also here, wire is also here. In this case, what is the angle between the wire and magnetic field? What is the angle between two parallel lines? 0 degree. If beta theta becomes 0 degree, if the current and magnetic field direction is the same, and the angle between them becomes 0 degree. In this case, the force that is applied beta is 0, or you can say it is minimum force. When the wire is placed at 90 degree to the magnetic field, there is maximum force. And when you place it parallel at 0 degree, then 0 force. There is no force. So when you place it perpendicular, here it is perpendicular at 90 degree. If you place it perpendicular, then maximum force. But if you place the wire parallel to the magnetic field, then 0 force. And if you place it at some other angle, then force is between. Here is at least, here the most, and between at some other angle. Is it clear? Come on, let's move forward. Question, CBSE 2023. Alpha particle enters, force experience. Tell me whether alpha particle is going like this. I told you what kind of charge in no alpha particle? Is it positive charge? So if positive charge is coming down, will the current also come down? Yes. The same direction of the current flow of positive charge. Come on, now we have to find the force. We use the right hand palm rule. Open the right hand palm. Where is it written to use Fleming's left hand rule? Open the right hand palm rule. First of all, finger where? In the direction of magnetic field. Is the magnetic field here? Yes. Thumb should be where? In the direction of current. Where is the current? Down. Flipped it. Take. Magnetic field with the finger. current with the thumb, force is coming where? With the palm. Palm is where? Out. So where is the force? Outward. Where will be the force applied? It is applied outward. Come on, let me do it with Fleming's left hand rule. Forefinger in which direction? Of the magnetic field. Done. Middle finger in which direction? It is automatically in the direction of current. Thumb is coming where? Out. And what do you get from thumb? Force FBI. Force is obtained from the thumb where? Outwards. So the option will be this. Out of the plane of the paper. Clear? Look next. Came in CBSE 2024. Made an electron run 2, made a proton 2. Now force is asked on both. It is very easy. If the electron is going up, where will the current go? Downwards. Yes or no? There's negative charge on electron. Where there's electron, current is opposite of that. If the proton is going downwards, then where would the current go? Downwards. Because where the positive charge flows, look at the proton, plus is written. If the positive charge flows, current goes there. Where the negative charge flows, current opposite to that. First thing is that both the wires, the current is in the same direction. It means force would be in the same direction in both. Let's find out. Right hand palm rule. First of all, in which direction are the fingers? Magnetic field. Thumb in which direction? Current. Where is it? Downwards. Where would the palm come? Outwards. So where is the force exerted? Outwards. Will it be same in both? Yes, in the both of them magnetic field. Use the left hand rule. In which direction is the forefinger? Magnetic field. In which direction is the middle finger? Current. Where is the thumb coming? Out. In which direction will the force be? Out of the plane of paper in both of them. Both pointing out of the plane of the paper. Is it clear? Chalo. Now comes the last topic of our chapter, domestic electric circuit. Domestic means they are talking about home, in our home. So from the electricity poles, 3 wires come towards our home. One is live wire, one is neutral wire, one is earth wire. Out of these, the most dangerous is live wire. Live wire is 220 volt. Other than this, the neutral wire and earth wire, what are they really both on? 0 volt and 0 volt. Live wire is generally red in color. Red means the color of danger. It's the most dangerous. It is a high voltage. Neutral is generally black in color. Earth wire is generally green in color. First of all, live and neutral goes outside our home. A fuse of electricity department is placed. It can be put inside the home too. It is such a fuse which you can't repair. Only electricity department checks it. There's a limit set of 50 ampere. Current more than 50 ampere will not go into your home. Why will not go? Why if this go more than that, then it's possibly you have to printing press in the house or you are doing some commercial use. So for that, Bijli rate is different. So go and talk to the department, then it would increase. Okay. After that, both these wires go in the meters. We can't touch these two. House at electricity meter, kWh, kilowatt hour meter. 1 kilowatt hour is equals to 1 unit of electricity. After this, from above, your earth wire is also coming. How are all these wires going? Parallel to each other. In each your room of your house, in each socket. How are the wires coming in parallel? Say this got 220 volt, this is to 220 volt, 1, 2, 3. Every socket of every room 220 volt. It means they are connecting in parallel. Why do we connect in parallel? I told you in the last chapter, there are a lot of advantages. What are the advantages? They are written here. First of all, what happens in parallel? Different devices get different current. What happens is the series current become the same in all of them. Now suppose you have to turn the fan, it would work on 4 ampere current. Suppose you have to turn on the AC, you need 15 ampere current. So different devices need different current, which is only possible in parallel. Second is independence of different device. If one device is damaged, then it doesn't affect the other. And the series, if one damaged, all are damaged. That's not a parallel problem. What is third point? All devices get 220 volt the potential difference. What happens in parallel? The potential difference is the same in all of them. That's why we connect them in parallel. The next comes our earthing. The symbol of earthing is this. If you see this drawn anywhere, understand that it has been earthed. What is earthing, beta? The heavy appliance in our houses and those which are metal body. Take the best example, the refrigerator at home. Many times you must have seen that when you touch the metallic body of your fridge, it gives you a current shock like that. Sometimes the fridge gives a shock. So earthing is done to prevent this. What is done in the earthing? That a wire is stepped like this from the metallic body. The step wire is attached here and taken and attached to a copper plate down in the earth. It's not just a copper plate. There is also salt and stuff there, a charcoal. Entire setup for earthing is created. So I took this wire and put it down. The whole setup with the copper plate is called the earthing setup. This is down. It is inside the ground. And the wire was attached to the metallic body after stepping it. Now imagine, if you have seen there are many wires behind the fridge. Suppose the insulation of some wire came off, meaning its plastic cover is removed. And that wire is directly touching the fridge. Brother, you are supplying electricity behind the fridge, giving current. Suppose some wire touched it. Now what will happen? Current will come in the entire body of the fridge. It's metallic. The moment you touch it, you are gone, brother. So what we have done, we have attached an earth wire from here. As soon as current came into the fridge, some cut wire touched the fridge, behind it some problem occurred, a fault happened. As soon as current came into the metallic body, where will all the current immediately flow? It will flow into the earth. Why does it flow? Because beta, this is a path of very low resistance. What is the formula of current? V upon R. The less the resistance is, the more current will flow. Less resistance, so more. So where does all current go? Into the earth. Earth beta is a mother. Take as much current as you want, give as much current as you want. So heavy current flows into the earth and you don't get a shock. The device does not get damaged. As soon as such a heavy current flows, your fuse blows. When the fuse blows, you understand that some fault has occurred. Then you repair it. So all these things are explained. Remember that earthing is a safety device. Earthing is EAR. Earthing is a safety device. How does it work? That's what is told. How does it save us? One, it saves us from the electric shock. Second, it saves from the damage to appliance. That's the whole story is written. Okay, let's move forward. Next beta is overloading. Overloading means, don't we say sometimes that today I eaten a lot, it become overloading. This truck has overloading. It means to give more than the necessary. When some device says that I only need this much, but you give so much current, then we call this overloading. More current than that, it can't take. When electric circuit has more current than it can safely handle, the amount that it can handle, you can give it more current than that. That is overloading. Its biggest prime example is short circuit. Remember, this is arts can exam. What is short circuit beta? Short circuit means small circuit. Suppose there is a live wire coming in the house and from somewhere is a neutral wire is coming. How much potential on live? 220 and 0 on neutral. There are two wires. A bulb is connected to these two wires. The current had to go like this and return like this, passing through the bulb. What happened? Somewhere the plastic cover of both wires opened in the middle. It happens many times, right? There are two wires touch either. Does it happen or not? The plastic cover open and both wires negate their test. As soon as they touch here, the current will say, hey, Babu, why should I go ahead? There is a resistance. What is a bulb? It is a resistance. Why should I go path in the resistance? I see a small path. The wire has tell directly copper wire, saying current will flow. Great. From here, it will be pure enjoyment. All the current flows from here. And how did this path become? A path of extremely low resistance. There is no resistance at all, bhai. If it went from the bulb, it would get some resistance from the bulb. No resistance here. A small path, a shortcut. That is why what is called short circuit. Small path, breaking that path, the current exited from itself. Now I just assume that suppose this copper wire's resistance is very low. So I said how much will be the current? What is current? V by R. I just assumed it like this. This is an example, don't write this. How much is the potential difference by? 220 volt above, 0 in this. So when they touch, there will be 220 volt here. Here it will be 0. So difference will be 220 volt. I assume the resistance of this wire will be very low, 0.0001 ohm. So by how much current flowed? Or a pop. So much current, very heavy current. Okay, when such heavy current flows, we studied in Joule's law that there is heating. Heating effect of current, H is equal to I square RT. We read it in Joule's law in the last chapter. So beta, what will happen? There will be lot of heating here. The more current, the more the heating will be. So a lot of heat will develop here, and what will happen of this? Fire breaks out. Okay, so this is the problem of wood loading. What is the second example? Too many appliances connected to a single socket. Many times you bring this, what do we call extension plug? That we bring it. Many times it happens that electric socket is very far off the bed. So we bought it. Papa also plugged in the mobile charge. Also you plugged in. Mom also plugged in. Arey bhai, this socket also has its own capacity. Inside I can withstand up to a 7 ampere current. Everyone is plugged and drawing it and 10 ampere of current. So what will happen? A very heavy current is flowing through it. So what happened? Overloading happened. Why is it overloading? As much as it could safely handle. 5 ampere. You are asking 10 ampere from it. So what will happen? Such heavy current will flow. Heat will also produce. Hair will break out. The third thing is a sudden hike in spike voltage. Now this is not your fault. Suppose the electricity department that sends current to your house sends it a very heavy voltage. The electricity that is generated is a very high voltage. It is slowly brought down, step down and brought to your house. Suppose at some step it happened that a transformer did not work. Many transformers are installed. Where electricity is being generated and your house is coming, there are many transformers in the path. One transformer did not work and the step down did not happen. The potential did not decrease. So heavy voltage came. They don't say a sudden high supply came. Today there is a high voltage at home. High voltage happened. Is there high voltage? The current will also become very high. I is equals to V by R. Voltage high, so current high. Right? Ohm's law. V is directly proportional to I. The higher the voltage, the higher the current. This is also an example of overloading. If the current is so high, heat will be produced again and it will burn. The way to save all this, in the previous chapter we studied fuse, a phase safety device. What do we do with the fuse? We install it before appliance. Suppose this appliance is saying I cannot tolerate current above 3.5 ampere. This is TV saying that maximum current I should be given is 3 ampere. I cannot tolerate more than this. Nowadays, for example, the TV has one fuse inside. This is an old story. Let's understand the basic method. So I said TV will not be able to extend from 3.5 ampere. So I installed a fuse before it. Max to max 4 ampere, right? We can install 3.5 ampere. We can also install 3.8. Max to max 4 ampere. Now suppose current came from here 2 ampere, it will say no problem. It will say current came 3 ampere, it will say go, no problem. Current came, let us say 4.5 ampere, it will say stop, we will burn out, why won't we handle it? What is the capacity? 4 ampere. As soon as current above 4 ampere came, like 5 ampere came, this fuse wire will burn out. The function of a fuse is to burn out. It will die itself, it will save the TV. How does the fuse wire die? Which concept is it based on? Heating effect of current. This is the wire of fuse beta, right? Current came here. Upon coming of the current, what would be made? Heat would be made. What does the Joule's law say? H is equals to I square R into T. Current increased. Current came more than it can handle. So too much of heat produced. If heat is made, then it gets melted. If it melts, then the device is saved. The same thing is written here. Fuse wire is made of alloy of copper and tin. Alloy of copper and tin or lead and tin. Bhaiya, lead is very poor conductor. It's made of it. Fuse wire is never made of pure copper. Suppose they ask in an exam, why fuse wire is not made of pure copper? Because copper is a very good conductor, bhai. It would pass all the current. Fuse wire is made of poor conductor. Make such an alloy, tin is put. Tin is poor conductor. They put lead and tin. Say this one is given in the NCERT, so much memorize it. Fuse wire is made of copper and tin or lead and tin. You can write whatever you want. What should be the specialty of fuse wire? There should be two specific things. First, low melting point, so it melts. Suppose it is a high melting point, that heat would be generated. More current came, heat was generated. There was a lot of it. It is not melting at all. It is not melting, current is going forward. So it's necessary to melt, low melting point. The job of fuse is to burn out. Second thing, high resistance. It should not be good conductor. It should have high resistance. Why should the high resistance? Heat, look at the formula. H is equals to I square R into T. The more the resistance, the more the heat will be generated. The more the heat is in it, the sooner it will melt. Suppose we had used a pure copper, then would have no resistance. Not enough heat would have generated. So the fuse should have low melting point so that melts. High resistance so that what happens? Lot of heat is produced. The job of fuse is to burn out. Clear? Come on. Now you have some high rated devices at home. They are heavy devices such as geyser, right? Such as iron, such as toaster. The fuse is installed. Its fuse rating is a bit heavy. It has a 15 ampere fuse rating, meaning it will at least this much current pass. At most it won't like pass. There are many devices which are low, meaning low device power rating, such as bulb, fan, TV. All this work done in 5 ampere, fan, TV, fan. So the fuse installed in this 5 ampere, meaning don't give current above 5 ampere. Okay. CBSE 2023 hours wiring with 15 ampere current rating in domestic electric current is for 15 ampere. One is used for what? High power rating such as geyser. Next 2020, in time of short circuit, the electric current in this circuit, what will happen? What happens in a short circuit? A small path is formed. What flows through it? Heavy current flows. So what happens to the current? Varies continuously, does not change. What happens? Increases heavily. What flows beta at the time? Heavy current flows at the time of short circuit. Okay. Okay, beta, lecture ends here. The winners of the correct answer of our previous reproduction lecture are Majestic Ranjit. Our winners are Kunal Singh, Ankush Kumar, Danish, Adil, Syed Hacker Raja, Garv the all-rounder, Neil K0, Sakshi Tomar. All these people are winners. Huge congratulations to everyone. Let's you will win in this lecture. The chapter ends here. Keep studying. All the very best.